All right. Hi everyone present and everyone online. So far, we've learned about how we're going to how you calculate the electron-phonon interactions, specifically this G matrix that David talked about in the last lecture. But of course, the main point of Perturbo is to actually calculate transport properties. And so that's what I'm going to kind of go over now and like what this last part of this Perturbo model, the Perturbo.x, does. Ooh. Let's see if I can actually control this. Here we go. All right. So as Marco talked about in detail, Perturbo is able to accurately calculate phonon-limited transport properties in a broad class of materials. And some of these are shown here. Marco, of course, went into much more details about this, so I won't elaborate on this point. But in general, Perturbo can calculate electrical properties such as conductivity and mobility, magneto transport properties such as the Hall factor, and thermal transport properties such as the Seebeck coefficient. And what's especially interesting in Perturbo is that because we can kind of look at each individual phonon modes, we can understand what gives rise to the various transport properties and what's like the dominant scattering mechanism. So we want to calculate transport properties. And so the main equation to do that is, of course, the Boltzmann transport equation, or BTE for short, which is shown in its full form here. Now, the key component is, of course, F, which is the electronic occupations of states labeled by band N and momentous K. And then we want to calculate its evolution in time. So it has this time dependence. And in its full form, the BTE has an explicit time dependence, as well as drift terms due to a spatial gradient and due to external fields given by this capital F right here. And then it also includes, of course, internal collisions, which is given by the collision integral, this I right here. Now, in general, you can include any sort of scattering process you might want. In this lecture and in general in this workshop, we're going to focus on the electron-phonon scattering, but you could also include electron defect scattering and also electron-electron scattering, for example. And of course, the reason we focus on electron-phonon scattering is because this dominates at higher temperatures, such as room temperature, whereas electron defect and especially electron-electron only comes into picture once you're at lower temperatures, and in the case of electron-electrons, in correlated materials specifically. So in order to calculate transport properties, we need to solve the BTE. Now, this is, of course, an extremely complex equation to try and solve. So to calculate transport properties, we do some simplifications. The first is that we study systems that have reached steady state. This means that we don't look at systems that have like been perturbed and then look at the immediate effect afterwards. That's what we call ultrafast dynamics, which Kelly will discuss later in the workshop. But in the case of transport properties, we look at the steady state where the system has reached an equilibrium between the perturbation terms, such as the drift terms, and the collision terms on the right. And so this means that we effectively end up with this remaining equation for the BTE. And in our case, we make further simplifications in that we, in the spatially dependent term, only consider temperature gradients for the thermal conductivities. And then for the external fields, we consider electric fields as well as magnetic fields for the magnetic transport properties. And then in this lecture and generally in this workshop, we will only consider the electron-phonon collision integral on the right here. Now, the next thing we do in order to solve this BTE is that we assume these perturbations to be relatively weak. And that means we can do a linear expansion in this occupation factor F. And what that means is that we take it to be described by its equilibrium distribution, which is, of course, the Fermi-Dirac distribution for electrons, as well as this small perturbation delta F, which is proportional to the perturbation strength. And this is sort of described as this very, very simple diagram right here, where in equilibrium, where you have no perturbations, i.e. no external fields, no temperature gradient, the electrons have a Fermi-Dirac distribution, which is kind of described by this gray circle. And then once you apply perturbations, it's going to be ever so slightly deviated from that perturbation, like kind of shown with this blue circle right here. So the first thing I want to talk about is how we calculate electrical conductivity. And so in that case, we ignore spatial dependence and only consider a uniform electric field, which means our BTE further reduces to this expression right here. We then go ahead and linearize it using this assumption of a weak electric field. And that means we basically just plug in this into the BTE, and it reduces once we only keep terms up to linear order in the electric field. We end up with this equation right here. Once we solve this equation for the delta F, which is the perturbation, we can then plug this into the equation for the current density. And of course, the current density will only depend on the deviation from equilibrium, namely the delta F, because of course, at equilibrium, where you have no external electric field, you will of course also not have current density. Therefore, there won't be an F0 in here. So then once you calculate the current density, you can then extract the conductivity tensor. So that's kind of the general overview of how you would go about calculating conductivity. But in reality, there's multiple methods of doing this. So the most simplistic method of doing that is to use the relaxation time approximation. And what the relaxation time approximation does is that it approximates the electron-phonon collision integral into this very, very simplistic form here. Now, the kind of physical intuition behind this is that we have a constant relaxation time. If you were to kind of instead look at the time dependence from the Boltzmann transport equation, you would in fact find that if you just put the explicit time dependence as well as this RTA approximation for the collision integral, this would give you F with an exponential decay given by this tau, so that basically this tau basically is the time between scattering events that gives a decay of your occupation factor. Now, going back to this form of the Boltzmann transport equation that we're trying to solve, which has the external electric field, you can then rearrange this equation and end up with an expression for the delta F, which is the perturbed occupation. You then take this and plug it into the expression for conductivity, for the current density, and extract the equation for the conductivity. And as you can see, this now depends on this constant relaxation time tau. So that method is what's usually done in very simplistic models, such as toy models. And this constant tau is often found by fitting to experiments or using some very simple theories to kind of give a value for this tau. However, it turns out that this having a constant tau for all possible bands and momentars of your electrons is not exactly correct. So this plot right here, which shows gallium arsenide and the relaxation times, you can see that the relaxation time actually varies by orders of magnitude with respect to momentars, which is given by the different values right here, as well as energies, which basically goes over different bands. And as you can see, this very drastically changes the relaxation time. So therefore, having one constant relaxation time for all your possible states is not particularly accurate. So therefore, in Perturbo, we instead calculate a state-dependent relaxation time, namely this tau of nk. And the exact expression for this, or rather the expression for the scattering rate, was just 1 over tau, or the inverse of tau, can either be derived using Fermi-Golden rule or many-body theory, where the scattering rate is the same as 2 times the imaginary part of the self-energy, where the self-energy is taken to the lowest order, i.e. the first diagram, which is this one. Once you do that, you end up with this rather large expression for the scattering rate, where, of course, this G is the electron-phonon interaction matrix, which is what David described on how you get from DFT and Vanier 90 calculations, and then is interpolated in QE to PERT. The other parts of this expression is this n factor, which is the phonon occupations, and this f, of course, is the electron occupations, and then we have these delta functions, which ensures energy conservation in the scattering processes. So Perturbo then goes about solving this equation, and once you have then the state-dependent relaxation times, you can then go about calculating the conductivity, which is now much more accurate because you have this state dependence, and because of this full expression, we also have a temperature dependence of our scattering rate. And of course, the key part again is that we're doing this from first principles, so you're no longer fitting to experiments. You're only just going off of the atoms in your crystal. So we can take this one step further. So far, I've only talked about the relaxation time approximation, which was a way of approximating this collision integral. However, in Perturbo, we've implemented it so that you can actually solve this expression using the full expression for the collision integral for the electron-phonon interaction. So to do this, we make an ansatz for the perturbed occupation, which we take to be this form right here, where we now have this unknown capital F. If you then take this and plug it into this expression and rearrange and do some algebra, you end up with this equation right here, which is a linear system for this unknown factor, capital F. And another component that comes into this equation is this W, which is the electron-phonon scattering probability, and is given its full form here, and is effectively the probability of an electron scattering between state nk and state mk plus q by emitting or absorbing a phonon with mode nu and momentum q. So as I said, this is a linear system and a linear equation, and so you could really use any sort of technique you want to use to solve this linear equation, but in Perturbo, we use an iterative approach. So in this iterative approach, we start with a initial guess for the capital F, which we take to be the RTA result. And so going back to this expression, you can see that actually, if you were to ignore the second term, you would actually just end up back at the RTA approximation for the delta F. And so this is what we take to be our first guess at this unknown capital F. We then plug this into the full expression for capital F. And with this new capital F, we then calculate the conductivity. We then check this against the previously calculated conductivity and see whether it is below, whether the difference is below a certain threshold. If it isn't, we go back and we repeat this process until we find that the value for the conductivity converges, in which case we finish our calculation and have obtained the accurate value for the conductivity. So all of that was to show you how we calculate electrical conductivity in Perturbo. But as I mentioned, we can also calculate thermal transport properties, such as the Seebeck coefficient and the thermal coefficient. So in the case of thermal transport, we, instead of an electric field, have a thermal gradient, namely this dT/dr. And so physically, of course, we would expect the electrons to move from a region of high temperature to a region of low temperature. So in this case, the BTE ends up in this term, where you've now ignored this term for the external fields, but you've now reinserted this spatially dependent term, specifically with respect to the temperature gradient. We can then basically do the exact same steps as we did for the conductivity calculations, namely that we first make an ansatz for the delta F, which we now take to be this, where we again have this unknown capital F. In this case, we call it tilde because it's with respect to the temperature gradient as opposed to electric field. And then we plug this into the linearized form of the Boltzmann transport equation and end up with this expression for this unknown capital F tilde, which again is very, very similar to what we had for capital F, which was the conductivity. And again, this first term is effectively the RTA approximation in this case. And as you can see, it's almost exactly the same as the case for conductivity. But the key difference is this energy factor. And this, of course, makes sense because in the case of thermal transport, we're transporting energy as opposed to charge. So to summarize, we can find a solution solution to the Boltzmann transport equation by linearizing it, by assuming that we have a weak temperature gradient or electric field. And we write the delta F in terms of this capital F as well as this capital F tilde. And these can be found either by calculating the RTA approximation or calculating the full solution using the iterative approach. And once we have these unknowns, we can plug them into the expressions for electrical conductivity or for the Seebeck coefficient for thermal properties. And so to give examples of this, we've done these calculations for gallium arsenide, where we calculate mobility both using RTA as well as the iterative approach with ITA, as well as the Seebeck coefficient in gallium arsenide. And you can see we calculate these for different temperatures. So that's a very kind of broad overview of what's being calculated in the transport part of Perturbo, specifically the Perturbo.x of the code. But so far, I've only really described the theory and the equations that we're calculating. But there is, of course, technical details to this as to how you go about actually converging your calculations and obtaining the correct results. So the first thing I'm going to look at is, or talk about, is the scattering rate calculations. So going back to this rather long equation for the scattering rates, there are some key parts to notice. The first is that we do a sum over electron bands, as well as phonons modes and phonon momentous Q. And the key one here is phonon momentous Q, because it turns out to be able to converge these calculations, you need a very, very large number of Q samples, usually way larger than 10,000 Q points. And so this means that how you sample these Q points becomes very important. And in Perturbo, there are two ways you can do this. Either you can create a regular Q grid in the first Brillouin zone, or you can randomly sample the Q points using Monte Carlo algorithms. And in this Monte Carlo algorithm, you can either choose to use a uniform distribution or an importance sampling using Cauchy distribution, for example. And the latter is very important for polar materials, where you have to have very, very fine Q samples around the gamma points, which I will get back to in a second. Another part of this expression is the delta functions, which we implement using a Gaussian function. And of course, the Gaussian function is given here, as I'm sure most of you are familiar with. And it has this broadening parameter, which is one of the inputs to Perturbo. And it's called smear. So you set that in order to convert your calculations. Now, another common choice in order to express this delta function numerically is to use a Lorentzian. However, as shown as this diagram here, it turns out that for the scattering rate calculations, using the Gaussian expression makes our results converge much more quickly. So coming back to this point about Q sampling, as both Marco and David talked about, this electron-phonon interaction, especially in polar materials, has a long-range part and a remaining part, rather a short-range part. And as they both mentioned, the long-range part goes as 1 over, I think this should be 1 over Q, as opposed to Q squared, so I'm sorry for that. But in any case, what this means is that as Q goes to 0, this diverges. And this means that when you actually try and calculate this numerically, this is not a very well-behaved function. And it means that you need to sample much, much more finely in this region near Q equals 0 in order to actually get it like how your function looks like when it diverges. But of course, we would ideally like to not have to sample Q very finely everywhere, because it's actually very expensive for us to do so, both in memory and of course in calculation time. So therefore, in Perturbo, you can split these two up when you calculate the scattering rate, and you can use different types of samplings for the long range and the short range part. So in the long range part, where we have a diverging function, we use importance sampling so that you can sample it using the Cauchy distribution, which will be much, much more helpful to kind of visualize your diverging function. Whereas in the short range part, you can then still use a uniform sampling and have much, much coarser Q samples. And so in this way, we really optimize our calculations for how your electron-phonon interactions look like. And as you can see in this diagram right here for gallium arsenide, you can see that both the long range and the short range part are actually very important in order to model your relaxation time in gallium arsenide. So another thing that's important in the implementation of this is to try and optimize both memory and speed, because it turns out that this electron-phonon matrix is very, very, very large, especially once we've interpolated it, as like David talked about, you need like 600 cubed K grids as well as Q grids, and it becomes extremely, extremely large. So we have multiple ways of kind of attacking that problem. The first is that we look at the scattering events, and that means basically like KQ pairs. So we look at, okay, I start with a K, I scatter with the Q momentum phonon, and I get a K plus Q state. And then I look at, okay, in the scattering event, do I satisfy energy and momentum conservation? And if I don't, then I'm not even going to account for that scattering event. So basically, we only store scattering events that conserve energy and momentum. So this already reduces quite drastically how large, like how many points in this matrix we actually need to store. But even so, it's still pretty large. And so this is where we use parallelization as well. And so the first thing we do is that we use MPI parallelization. And in this way, we basically take each of these like scattering events, i.e. the KQ pairs, and we place them over different nodes in our cluster. So each node has a separate set of KQ pairs. And then each of them calculate the scattering matrix elements, G, as well as this W in the case you're using the iterative approach. And then each of them go about calculating their contribution to the scattering rate, as well as this unknown F. And then at the end of that, you then do an MPI sum to then like compute the sums then over the different nodes as well. So that finally you end up with an expression for the scattering rate, or the capital F, that has summed over all KQ pairs. In addition to that, inside these nodes, we also do an OpenMP parallelization so that you can like parallelize over the different threads within each of your nodes. And this is just to speed up the calculation of the sums over the KQ pairs that are in each node. And so by doing this sort of parallelization, we not only make our computations much faster, but we're actually able to actually store these large matrices because each of the G's and W's are only stored on each of the nodes. So that gives you some details about the calculations for the scattering rates, as well as the unknown capital F. But of course, we also want to calculate conductivity. And so there are technical details to this as well. And one of them is that this part of these expressions, this delta, this dF0dE at lower temperatures actually, or even at room temperatures sometimes, becomes almost like a delta function, as you can kind of see here. And this means, again, that to be able to actually like converge these calculations, we need finely sampled points in this region of energy. Now, of course, the limiting factor in our calculations is the calculation of the relaxation time and this unknown capital F, because this is a very large computation, as I said previously. And so therefore, in order to do this, we basically split up this expression for the conductivity into these two parts, namely this energy integral, as well as this transport distribution function. And what this means is that you can do the sum over K using a tetrahedron integration, which makes this much more accurate without having to compute more, tau for more K points. And then once you have this expression, you can plug it back into the energy integral, and you can very, very finely sample this energy, which will allow you to model this delta-like behavior. Another key thing that we do in order to optimize these calculations is that instead of calculating the tau or the capital F for all K points in our Brillouin zone, we do it only for the irreducible wedge. So what this means is that a lot of these points in the Brillouin zone can actually be symmetrically transformed into this wedge right here. And so if you only calculate F or tau on these points, you can then use symmetry operations to find tau, for example, over here. And this, of course, reduces the computational cost drastically. So finally, the last kind of technique of implementation that I would tell you about is the definition of an energy window. And so what this does is that we know that at a certain temperature, only parts of our energy bands are actually going to contribute towards current, for example. Only electrons within a certain energy window are going to actually contribute towards current. And so this means that we can actually exclude a lot of the K points, because very few K points actually fall will actually give you energies at like within this energy region. And so what this means in your Brillouin zone is that we basically only calculate the K points within this green circle. And then further, we of course reduce that to this irreducible wedge within this green region. And so to give you some examples of how drastic of an effect this actually has is that, so if we start with the gallium arsenide with a K grid of 100 cubed, by just using the energy window, i.e. just using this green circle here, we go from 1 million K points down to 331 K points. If you then further reduce this using the irreducible K points, if you were to use the whole Brillouin zone without the energy window, you would have about 44,000 irreducible K points. But with the energy window, you're down to 30 K points in total. And similarly for the tetrahedron integration, this reduces it down from 6 million K points to about 1,300 K points. Now, once we want to calculate for the K-cube pairs, in the case of the scattering rate, this is an even more drastic reduction of points. So in this case, of course, we need to enlarge the energy window a little bit because we now have the energies of the phonons in addition. So as you can see, our green circle becomes a little bit bigger because we allow for the momentum with phonons to scatter us a little bit outside of our energy window. But if we now look at the K-cube pairs for a 50 cubed grid, initially, without the energy window, you would have about, what is this, like 1 billion K-cube pairs. But the key point is once you have the energy window, you are down to 2,000 K-cube pairs. And this is why we can actually even calculate these electron-phonon matrix elements and the electron-phonon scattering rates. So with that, I would like to conclude, but I would like to briefly mention some of the new functionalities in Perturbo, because of course, what I've talked about so far is, the baseline of Perturbo, but we're constantly updating it, as will be talked about in this workshop. So some of the new functionalities that have been released in version 3.0 is The deparallelization, you can now calculate spin relaxation time. There's also the ability to calculate ultra-fast spectroscopy. We've also implemented the cumulant method, which allows you to do transport calculations in materials that aren't well described using purely quasi-particle or Fermi liquid approximation. As we've mentioned a little bit already, Perturbo is now interfaced with DFT plus U and DFBT plus U. We've also included a quadrupole correction, and we've interfaced Perturbo with T-depth and SHA so that you can calculate for anharmonic phonons. And as Marco also briefly mentioned, in future releases, we're working on interaction compression using SVD as well as tensor decomposition. We're working on coupled electron phonon transport so that you can calculate phonon drag. We're also working on exciton phonon and magnon phonon interactions, correlated systems, as well as electron viscosities. And some of these will be touched upon during the short talks at the end of tomorrow. So that is the end of my talk. And do you have any questions?